Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the linear algebra guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Okay, so over here we have a system of three linear equations, and let's say that we are asked to find the solution to this system of equations, if possible. So let's try using Gauss-Jordan elimination and putting this matrix into row-reduced echelon form. I know you're probably comfortable with putting a matrix like this into row echelon form, but let's try changing our mindset to Gauss-Jordan elimination, and let's try putting this matrix into reduced row echelon form and describing its solution from there. Because it's a lot easier to see the solutions in reduced row echelon form, and it's the form you're probably going to use for the rest of this course. So starting off, let's just say we have a column for x1, 1, 1, 2, a column for x2, which is the coefficients of x2, 2, 2, and 4, a column for x3, 1, 2, and 0. And I didn't really need to write 0, x3 here, but I did because sometimes it is represented. And x4 is 1, minus 1, and 6. So this is our coefficient matrix, and we need to add on a column that describes what each of these equations are equal to. So this column would contain the values 7, 12, and 4. So we need to apply Gauss-Jordan elimination to this matrix in order to obtain a solution. So first, let's go ahead and circle the terms we want to make leading ones. So this 1 over here, this 2 over here, and this 0 over here. Now, in a matrix that isn't in a coefficient matrix that isn't perfectly square, it's possible that we end up finding other terms to be leading ones instead of these. For example, we might have a leading one here, and we might have a leading one here as well. But we're going to start off with the assumption that we have three leading ones here, and if we don't, we can go from there and we can see which terms will become leading ones. Because it is possible that one of these two terms is just eliminated. And if there's a 0 there when we get to it, that means that it's impossible to make that term a leading one. So we either leave the row or we create another term in that row to be a leading one. So I'll show you what I mean by that. But first, let's go ahead and let's complete everything related to our first leading one. So we already have our first leading one here, but to put this matrix into reduced row echelon form, we need to eliminate the both entries in the column that are non-zero. So this one over here and this 2 over here. So let's start off with the 1. To eliminate the 1, we go to the column with the 1 in it, and we find the leading one in that column. That's this one over here. So how do you use a 1 to eliminate a 1? Well, you can subtract them. So we can subtract row 1 from row 2 to eliminate this one over here. So let's do that. Row 2 minus row 1, and we want to substitute, we want to make this row 2 in our final matrix because that's the row that we're trying to eliminate a term in. So let's go ahead and do that, but first we have to, of course, rewrite row 1 just to show that it doesn't change, and it doesn't change because we're only affecting row 2 in our final matrix, so 1, 1, and then we add on a column with what all of these equations are equal to, 7. So 1 minus 1 is 0, just like we wanted. 2 minus 2 is 0. 2 minus 1 is 1, and minus 1 is minus 2. 12 minus 7 is 5, and the third row stays the same. So 2, 4, 0, 6, 4. Cool. So now we can move on to eliminating the 2 in this column. So we go up the column, we find the leading one. This is the leading one over here. So we somehow need to use a 1 to eliminate a 2. Well, 2 minus 2 is 0, so if we multiply this by 2 and subtract it from row 3, we should be able to eliminate this 2 over here. So let's do that. Row 3 minus 2 row 1, and we want to make this our new row 3. So the first two rows will stay the same because we're only affecting the third row in our final matrix. The third row will become the difference between row 3 and 2 times row 1. So 2 minus 2 times 1 is 0, because 2 minus 2 is 0. 4 minus 4 is 0. 0 minus 2 is minus 2. 6 minus 2 is 4. And 4 minus 14 is minus 10. Okay, so now we can move on to creating our second leading one. So we originally thought our second leading one will be here, but it's not. So if we don't have a second leading one in a row, we either make another entry in that row leading one, or we just leave the row as it is if it's all zeros. Here, since it's not all zeros, then we can have another entry to be our leading one. So we go across and we try making the next entry a leading one. So this entry over here. So this entry is already a leading one in this row, which is convenient. So we just need to eliminate the other entries in this column. This is very interesting, and I don't think we've handled a case like this before, so keep it in mind. When we don't have a leading one, when we don't have a term that we expect to be a leading one in a row, and this is usually when it's a non-square matrix, we move on to the next entry and we try to make that a leading one. If it's already a row of zeros, or there's 4 zeros here and like a non-zero here for this example, or in another example, if there's all zeros except the last term, that means there's no solution. If it's just a row of zeros, then that means that there's an infinite number of solutions. But here, since we can create a leading one, we do. So this is our leading one already, and it's already created for us. Sometimes it isn't. If there's a 2 here, I'd have to divide this entire row by 2. But lucky for us, it's already a 1. So we can move on to eliminating the terms in this column. So first, let's eliminate the 1 up here. It doesn't matter which one we eliminate first, but we still need to eliminate both non-zero terms in this column because we want to put it in row reduced echelon form. So let's eliminate this one. So we go down the column and we have to find the leading one that we can use to eliminate this one. This is the leading one. So how do we use a 1 to eliminate a 1? Well, we subtract row 2 from row 1, and that should do the trick. So let's go ahead and do that. So row 2 minus row 1, and we want to make this the new row, or sorry, my bad. I meant this to be the other way around. Row 1 minus row 2, and we want this to be the new row 1, because that's where we're trying to eliminate the term. So we would have 1 minus 0 is 1, 2 minus 0 is 2, 1 minus 1 is 0, 1 minus 2 is 3, 7 minus 5 is 2. We have to add on the column. Okay, and here this stays the same because we're only eliminating entries in the first row, and the third column, the same applies to this. Okay, so now we need to eliminate the last entry in this column, in other words, the minus 2. So let's eliminate the minus 2. Here we go up the column and we find the leading one in this column. The leading one is right here. So how do we use a 1 to eliminate a minus 2? Well, minus 2 plus 2 is 0, so we can add twice row 2 to row 3. So row 3 plus 2 row 2, and we want to make this the new row 3 because that's where we're eliminating the term. So the first 2 rows will stay the same because we're only affecting the third row in our final matrix using this operation. 0, 0, 1, minus 2, and 5. And so 0 plus 0 is 0, 0 plus 0 is 0, or yeah, minus 2 plus 2 is 0, 4 minus 4 is 0, and minus 10 plus 10 is 0. So here is the example of where we can't create a leading one in an entire row, so we just leave it as it is. Since this is a row of zeros, we just leave it as it is. Whereas here, we had a 1 we could work with, so we used that 1 to create a leading one, and it is already made for us. If this wasn't a 1, we would have to divide the row to make it a leading one. But yeah, so basically, we've reduced this matrix to reduced row echelon form. And the reason we can know that is if we look down the columns of the leading ones are the only non-zero entries in their columns. So this one right here and this one right here. But we're not done. The question asks us to describe the solutions to the system of equations, so we can do that by writing out each of these equations. So first, before we do that, we have to identify the free variables in our system. So free variables occur when their columns don't have a leading one. So the column of x1 does have a leading one, so it's not a free variable. The column of x2 is a free variable because it doesn't have a leading one. The column of x3 is not a free variable because it does have a leading one. And the column x4 is not a free variable, or it is a free variable, my bad. X4 is a free variable because it doesn't have a leading one in its column. So x1 has a leading one, x3 has a leading one, x2 and x4 don't. So we need to use x2 and x4 to describe the solutions of the system. So the first thing we'll do is we'll write out what our free variables are equal to. Let's make x2 equal to t, where t is some real number, because we need to make x2 a free variable. Let's make x4 equal to s, where s is some real number because x4 is also a free variable. And we can now describe the solutions for x1 and x3 in terms of these free variables. So x1 plus 2x2, well 2x2 is just 2t because x2 is equal to t, plus 3 s because it's 3x4 and x4 is equal to s is equal to 2. Now we can solve for x1, and x1 will equal 2 minus 2t minus 3s. So this is a solution to x1. We can also circle the solutions to x2 and x4. And these are just equal to some variable because they're free variables. So now we can find a solution to x2. Or sorry, x3. So x3 is equal to, well, it's equal to, x3 minus 2s is equal to 5, so we can solve for x3, and when we solve for x3, we get that x3 is equal to 5 plus 2s. So these are our solutions to our three variables. The first step that we did when we were writing our solutions is we just set our free variables equal to t and s. And then after that, we used t and s to describe the solutions to all of our variables. So this is an example of a system with infinite solutions because we have free variables. If there was a row of zeros and something that was non-zero here, like let's say 3, then that would be an example of a system with no solutions, because this equation right here would be 0 is equal to 3, which is just never true. But that's just an example. Here we had infinite solutions.